Hello everyone, welcome to It's All About Economics, and today's topic is frequency distribution and its graphic and diagrammatic representation. And this belongs to a paper, Statistical Methods, and just from Unit 1A. I'm Suraj Sharma. For more details, you can email or you can text me. So, what are the objectives? In last class, we have gone through what is statistics. We briefed about observations, population, and sample. Then we got to know about variables and types of variables, different methods of data collection, and the classification and tabulation of data. Similarly, now in this class, we'll be going ahead with frequency distribution, types of frequency distribution, and its graphical and diagrammatic representation. So before going ahead, we'll have to see some basic points. We'll have to get it by an example. Suppose we have marks of 100 students obtained in an internal assessment, and that is out of 50. We can write 50 students numbers or the marks like this, but we have no idea or meaningful idea if we write it like this. So first of all, what we do is we sort it in ascending order. So what does it mean by sorting in ascending order? Is putting the smallest value first, then subsequently the numbers from smaller to the largest one. Then we can make frequency table. This is frequency table, like if someone has got 10 marks, then how many of them have got 10 marks. So we'll put frequency before that. Like if this in this example till 17, we can see that only one student have got 10 marks out of 50. Then if we talk about 12 marks, four students have got 12 marks, so 4 would be the frequency for this particular value of x. And as like this, we can make frequency table for 50 students. Now, the basic points what you need to know is the class intervals. We have gone through this in the earlier class, that what is inclusive type of class. For example, the marks can be classified as 10 to 14, 15 to 19, 20 to 24, and so on. And this is called inclusive type of class intervals, where there is not a smooth shift from one class to class interval to the other class interval. And if you see that what is the size of the class interval here is actually 5. So 10 to 14, 15 to 19, and so on. How you calculate the midpoint? If you want to calculate the midpoint of this class interval, you just have to do is you add up the lower limit and the upper limit of the class interval and divide it by 2. So for example, for this class interval, the midpoint would be 10 plus 14, that is 24, divided by 2, and you'll get 12 as the midpoint for this class. Now what about range? Range is actually the difference between the maximum value and the minimum value in a sample. As far as this data is concerned, if we talk about this data, the maximum is 40 and the minimum is 30, oh sorry, 10. So the range would be 40 minus 10, that is 30. Now, if we talk about continuous data, it moves from one class to the other without a break. But as we have in the earlier example, that with discrete data, it moves with a break. Like if you see that if we talk about marks, and if it is in discrete number, then there would be a break. Like there is a break between 14 and 15, between 19 and 20, and so on. This would be particularly would not be true for a continuous variable. For example, if we see age, income, all these variables moves without a break because they're continuous. These are continuous variables. So for continuous variables, we have continuous frequency distribution, and if we are dealing with continuous variable, then we would be we should be having exclusive type of classification. We cannot classify continuous variable in inclusive type of variable. Why is this? Because, for example, if we have age data, then classifying the age as 10 to 14, 15 to 19, and so on, we would be ignoring the persons aged between 14 and 15, 19 and 20, 24 and 25, and so on. So in this case, we would be needing an exclusive type of classification such as 10 to 15, 15 to 20, 20 to 25, and so on. If you don't have this type of classification, you can make inclusive type classification, continuous one, and we'll let you know that how we'll do it. And lastly, it's very important to plot the distribution as to see how one distribution is very different or similar to the other. Next, how we can plot it, or what is frequency and its distribution. We'll be having a simple example here. Suppose we want to study the employment opportunities and the starting salaries of university graduate with an MBA degree, and we have data on 100 MBAs starting salary per month, like 55,000, 65,000, 60,000, 63,000, and so on. Each observation may have occurred once or more than that in this particular sample. So suppose there are 3 students who were offered with rupees 55,000 per month package, then the frequency of occurring 55,000 is 3 here, and so on. So this is what frequency is. Now, this data may be in the form of group or in the category, like those who are offered below rupees 50,000, 55,000, those who got it between 55 and 70,000, those who are offered above 70,000 per month salary. In this case, we get grouped frequencies. In the earlier example, we have seen these were not grouped frequencies. These were not group frequencies. And if we make groups, or we make classifications, or we make classes, or we categorize, then we get group frequencies. Now it can be asked that whether students were employed or not after graduating. So we can have answers in yes or no, or or can be asked that what is the sex of the employed students, and we can have answers in male or female. Next, what is absolute and relative frequency? So, taking an example of discrete data, suppose we have 100 graduates employed, and in those 60 were male and 40 were female, then 60 and 40 are actually the absolute frequencies. And what about the relative frequencies? We can calculate relative frequencies by this formula of the absolute frequency of a particular group, dividing it by the sample size. So here the sample size is 100, and for male, that is a particular category, we have absolute frequency of male as 60. So 60 divided by 100, and we get 0.6 in proportion, or if you want in percentage, you can multiply it by 100 and you'll get it in percentage terms. So 60% for males and 40% for females. This is the relative frequency. Now, for grouped continuous data, what would be the frequency distribution? We can have the earlier example of group or categorized data of monthly package, and you can see that here, if we see that here are 3 different classes, and these are denoted by AJ. Then we have absolute frequencies NJ. What is J here is the number of classes, and if you see that n1 would be the absolute frequency for class 1, n2 would be the absolute frequency for class 2, and n3 would be the absolute frequency for class 3. Now how we will calculate relative frequency? We'll calculate relative frequency by using absolute frequency of a particular class, dividing it by the total sample, that is n. And how we get n? We get n by adding the absolute frequencies of each class, means n1, n2 and n3. So we'll add up n1, n2 and n3 and we'll get n. This is how we get n. This is the formula for that. You have to sum different nj's, and this the value of j can go up to k, or how many class intervals are there. Then for calculating relative frequency, what you do is you divide nj, or a particular absolute frequency, by total sample. And if you add up the relative frequencies, all the relative frequencies, you will ultimately get 1. This is only because you are taking the fractions of all these things, and if you add up these fractions, it will add up to 1. So sum of relative frequencies will always be equal to 1. As you can see that here, the relative frequency of class 1 is 0.3, 0.45 for class 2, and 0.25 for class 3. It means 25% percent sample are getting above 70,000 package. 45% are getting the package between 55 to 70,000, and 30% are getting the package below 55,000. Now the graphical representation, and we'll start with the histogram. First of all, very important to know that for an ungrouped frequency distribution of a variable, we assume that frequency corresponding to variate value x is spread over the interval x minus h by 2 to x plus h by 2, where h is the jump from one value to the next. This is very particularly important when we have ungrouped data. And if we have ungrouped data, there would be a large number of variables, and x will change very rapidly. That is why we assume this thing. For plotting histogram, frequency distribution should be continuous. You should know that. If not, then we make it continuous. For example, we have marks obtained here, as we took the earlier example, and this is from 15 to 19, 20 to 24, and this is of inclusive type. Now for plotting distribution of a plotting histogram, you will have to make it exclusive type. You have to modify it, and as you have to modify, you will modify using this formula. Here d is the gap between upper limit of any class and the lower limit of the succeeding class. The upper limit of any class, let's say this is 19, and the lower limit of the succeeding class is 20. So what is the gap between 19 and 20 is 1. So here d is 1, and if you divide d by 2, then you will get 0.5. So how you will get the class boundaries? For upper class boundary, you will add up 0.5 in upper class limit, and for lower class boundary, you will subtract 0.5 from lower class limit. Like here, if we have lower class limit, you will subtract 0.5, you will get 14.5, and you will add up 0.5 and 19, you will get 19.5. So this is how you make it exclusive. And now you have these frequencies of 250 students. So these are the marks of 250 students. Now accordingly, you can plot this using rectangles proportional to frequency of corresponding class. Okay, so the height of the rectangle would be proportional to the frequencies. So you can see that the height of the rectangle will be maximum here in this class, because the frequency is maximum here. And so on. So, and you will be having frequencies on y-axis and class interval on x-axis. For example, you can have this histogram which is made by using quintiles of monthly per capita expenditure of a sample, and you can see that if we talk about quintiles, so it will 5 quintiles, then it will divide the whole sample in 5 categories, and there is a jump from 1 to 2, so there is a difference. D is 1. That is why if d is 1, then d by 2 is zero point 0.5, and the class would be like this: 1 minus zero point 0.5 and 1 plus zero point 0.5. So the class is actually from 1 zero point 0.5 to 1.5, and this is the height of this rectangle, and it is, you can see, it is proportional to the frequency of corresponding class, and not to the fraction of the class. However, if the width are unequal, then the height of this rectangle will be proportional to the frequency, to the ratio of frequency and width of the class. This you will have to remember. Now, continuing this, we can have a more example. You can have a data set like this of, let's suppose this is the marks, then frequency distribution can be made like this is the lower limit, this is the upper limit, and you can see that the range is from 101 to 300, and this is data of 50 students, and these are the corresponding frequencies. Same like you can make class intervals from 101 to 150. The frequency is 12, so 12 students are getting marks between this, 14 students are getting marks between 151 to 200, and so on. You can make bins, and what does it mean by bins? Bins is the upper limit of the class intervals, and 150 200 the corresponding frequencies, and similarly you can plot histogram using this data in Excel. Now, what is frequency polygon? Polygon is nothing but it can be made using histograms, and we have seen taken the earlier example of histogram of 5 quintiles of MPCE, and what you have to do is just take the midpoints of these abscissa, and join it by these straight lines. These are not straight as I have draw it, but you will have to make straight lines using using your scale, and you will add in last, you will suppose that there would be and another class of the same width, and you'll take the midpoint of that and you will add it, these 2 points with a straight line. So this is frequency polygon, and for group data, the abscissa of the points are mid values. What we have taken is the of each class intervals. Now, lastly, we'll talk about empirical cumulative distribution functions, which are very famous for plotting different distributions. What does it mean by cumulative distribution? Is actually we accumulate each and every frequency, a relative frequency. Now, this is another approach to summarize and visualize frequency distribution of variables, and it gives an idea about cumulative frequency distribution up to a certain point. You can see the earlier example, like we have data on 100 MBA graduates, starting salary per month like x1, x2. These are the values, different values of x. It will it may go to xn, and here n would be 100. Now you can sort the data, and you can order the data, like 55,000 is the minimum here, 60,000 and 63 and 65 and so on. Then what would be the ECDF? And you can define it by fx is defined as cumulative relative frequency of all values aj which are smaller or equal to x. So fx would be defined using this. So these are the relative frequencies, and you will sum all the relative frequency. That is why it is called cumulative. uh, as you can see that this would be from 0 to 1, because if we add up all the relative frequencies, if you add up it to up to a certain level, it would be from 0 to 1, would be ranging from 0 to 1. In case it would be 0 when x is tending to minus infinity, and when x is tending to positive infinity, the value would be 1. So it is a right continuous distribution. Now we'll take an example ECDF for ordinal variables. If we have data, consider we have 21,116 children's health assessment level by parent on a scale of 1 to 11. So we have a scale data. So this is an ordinal data where 1 is the least and 11 is the highest reported health assessment. And for fj, this fj can be calculated as f1 would be capital F1 would be small f1, f2 would be f1 plus f2, then f3 would be a small f1 plus a small f2 plus a small f3. These are all relative frequencies, small f's, and this is the ECDF, and so on. So if you want to have ECDF up to class interval up to health assessment of 6, then you will add the relative frequencies till this. So you will have 24.25. So this is how. So health reported health assessment up to 6 scale is 24.5% children have reported this. So this is how you actually interpret it. Now ECDF can be used to obtain relative frequency of certain values or intervals, like these are the health assessment from 1 to 11. These are the absolute frequencies of 21,166 children's, and this is the relative frequency. How we got it? We divide 486 by the total sample. Subsequently we divide 420 by total sample, and so on. This is how we get a relative frequency. Now if we talk about ECDF, then for class 1 the ECDF will be would be the same, that is relative frequency. Then for f2, this would be f1 relative frequency of class 1, and class 2, that is 4.28, that is the add-on of 2.3 and 1.98. Similarly you can add up to this and it will go up to 100%, or if we see that this may go up to 1 relative frequency. Now if we plot this data, and we have plotted it for you, then here in the y-axis you are having the cumulative distribution function, and here you are having children's health assessment. As you can see that for class interval, it's starting with 1. So for class 1 it is assumed that the distribution is uniform. So for 1, this is the percentage of you have 2.3%, or you can write it in proportion as 0.023. So 0.023 would be here. Then this is because it's an ordinal variable and in a discrete form, so there would be a break. Then again for this is for class health assessment scale 2, scale 3, scale 4, scale 5, and so on, and ultimately it is reaching up to 1. ECDF for continuous variables is very different from the ordinal or categorical variables. Let's suppose we have data on age. It may be in continuous form, or it may be in grouped form. If it is available in grouped form, then assuming that observations within each group or interval are distributed uniformly over an entire interval, and the ECDF can be defined as this. Here the fx is same. Here you will be having a complex formula. It will be the lowest value is 0 and the highest value is 1, and between 0 and 1 this is the distribution. Here k is the number of groups, then ej minus 1, this is the lower limit of, and ej is the upper limit of the jth interval. dj is the difference between the lower and the upper limit of jth class, or you can say this is the width of the class, and nj is the number of observations in the jth interval with fe0 is equal to 0. So distribution of the lowest class would be 0. uh, and this is the formula. You can calculate it by this. Simply we'll have an example by which you can easily get it, we have data on time required to solve a problem, and we have this distribution from 0 to 10 minutes, 10 to 15 minutes, and so on. This will, the range is from 0 to 60 minutes. Now these are the class 1, 2, 3, 4 until 11, and these are the ej minus 1 means the lower limit of this class, and the upper limit of this class. This is nj, or the frequency. So in the lower limit we have 0 frequencies, and so on. Then we have fj, that is how we calculate fj. As I've already told you that how you will calculate fj is by nj dividing it by n. So you can add all the nj's and you will get n. And how will you will get fj is by 0 dividing by the total sample, 11 dividing it by the total sample, you will get this, and so on. And what is fej? Simply you will have to add it, because it is cumulative, so you will add everything. So for class 15 to 20, this would be 0.4044 plus 0.04, that is 0.084, and so on, and this will go up to 1. So ECDF relates to a polygon chain that will connect the points like this: 0, 0, E1, FE1, then E2, FE2, and so on. To plot ECDF for grouped data, we can connect all FEJs and FEJ minus 1 with a straight line. And note that when the number of observations is very large, you have a large sample, then the length of the class interval becomes small, and when we join those small lengths, it looks like a continuous smooth curve. And for example, you can have this: if the observations, when observations are very large, it will look like a smooth curve. So this is an ECDF for large data set for long log of consumption expenditure. And this can also be plotted using the earlier given formula for a quantile of consumption connecting this. So if you have quantile of consumption expenditure like 1, 2, 3, 4, 5 quantiles, then you will have to add every point with a straight line and you will get the same. You can use this in comparisons, like I have plotted a ECDF for you. Here two distributions are there for log of hourly wages for men and women, and you can see that the distribution of female is lagging behind the distribution of male. This is the distribution of male, this is the distribution of log of hourly wages for female. So this is there is a big difference, there is an evident difference, visible difference between the log of hourly wages of male and female. This is how you can do comparisons. So thank you so much for being with me, and in next class we would be talking about bar charts, and other graphical representations of data. Thank you so much for being with me.